Hello once again, this is Tim Shu from San Jose State University, and I'm going to talk today about a big subject, a very important one, how derivatives affect the shape of a graph. So we'll start by finally asking, as we can now finally do, the central question of this class. We'll talk about the box, what the box is, and how that is one part of it, how f prime affects the shape of the graph. We'll talk about the first derivative test for maxima and minima. And we'll talk about the other part of the box, f double prime, and the shape of a graph. And we'll talk about the second derivative test for maxima and minima. We'll talk about inflection points, and we'll finally admit that we can't do everything quite yet, and we'll talk about what we cannot yet figure out about f given f prime. Okay, so what is the central question of this class? So here it is. The question is, if we know f prime, what can we say about f? That is the central question of Calculus 1. So this video discusses a qualitative answer to that question, not quite quantitative yet. All right, and so here's an example. So for example, suppose we have the graph of f prime given below. Here it is. And the question is, what can we figure out about the graph of f? What can we reconstruct up here to go with what we know about the graph of f prime? All right, so now let's talk about the box. What the box is, and this is sort of one of my favorite things about calculus, the box summarizes this entire class in a box. And here's the first part of it. Ta-da! There we go. Oh, all right, bye. Okay, no, and I'll say more about what this says, but if it's not clear what it says, let me say. This box says that f is increasing, upward slope, exactly when f prime is positive, and f is decreasing exactly where f prime is negative. So that's the box. So what does that mean in our example here? Well, if we indicate when f prime is positive by the blue part here, and when f prime is negative by the red part here, so that means that f will be decreasing for x between 0 and 1, and f will be increasing between 1 and 4. There it is. And that is, again, we see that f is increasing when f prime is 0 over here, and that f is decreasing when f prime is negative. Wow. So, just with that one rule, that one little box with 4 squares in it, we can kind of get a stick figure sketch of what the graph of f looks like, given what we know about f prime. All right, so turning to the first derivative test for maxima and minima, suppose f is a critical number for f, and remember what that means. That means that either f prime of c is 0 or f prime of c does not exist. So at any such critical point c, the first derivative test says that if f is increasing before c and decreasing afterwards c, then f has a local max at c. You can see that because, well, whoop, doop. Yeah, which means that the highest point, the local highest point is at x equals c. And if f is decreasing before c and increasing after c, that means that f has a local min at c, which again you can see from this picture. Whoop, doop. That sound effect is very important that you make that sound effect when you do this. And if neither of those cases happen, if you're increasing before and after, or if you're decreasing before and after, then f has neither a local max or local minimum at c. Or in other words, applying the box, and remember, let me remind you what the box says. Here's the box, this thing over here. So now applying the box, we can translate this top sentence into saying that if f prime changes from plus to minus at x equals c, then f has a local max at c. If f prime changes from minus to plus, from negative to positive, at x equals c, then f has a local min at c. And if f prime doesn't change sign at all at x equals c, if it goes plus to plus or minus to minus, then f has neither a local min nor a local max at c. All right, let's see, what does it tell us in our example? So remember, the critical number, we're sort of assuming that f prime exists for all values of x, even though it's not entirely clear necessarily from the graph, but let's make that assumption. So then the critical numbers of f will be where f prime is 0 at x equals 1 and x equals 3. So what does the first derivative test tell us about what happens at x equals 1 and x equals 3? Well, at x equals 1, f prime was negative before and positive after, which means that f is decreasing before and increasing afterwards, which means we have a local min of f at x equals 1. And at x equals 3, because f prime is positive on both sides of 3, and which means that f itself is increasing on both sides of 3, we have neither a local min nor a local max at x equals 3. So, in other words, what the first derivative test tells you is basically what you knew already from making this stick figure picture. It's just sort of codified now. So this list here, in a way, you don't really have to memorize this list. The point is that if you can draw this stick figure picture here that we have up here, then you can figure out where the local min and local minima and local maxima are for f. Great. All right, so now let's take the box to the next level. So the first thing to notice is that since f double prime is the derivative of f prime, that means that f prime is to f double prime as f is to f prime. So that means what we have in this box up here, we can copy over to these boxes over here. So that is when f double prime is positive, f prime is increasing. And when f double prime is negative, then f prime is decreasing. And then we observe, first of all, that when f prime is increasing, f is what's called concave up, or the more technical term that I prefer is smiley face. And let me sort of break out of the frame here to tell you why. So to say that f prime is increasing means that, for example, you might start off with f prime negative. Here's a curve with negative slope. And then as x increases, f prime increases, which means that you get a smiley face. And similarly, when f prime is decreasing, well, for instance, you might start off with a large positive f prime, and then as x increases, again, the sound effects are very important to have there. Anyway, so f will then be concave down, or frowny face. That gives us the full box. So there it is. That's really all you need to know. I mean, it's not all you need to know about Calculus 1 in a box, but it's pretty much. You can pretty much figure out the rest of it from there. I mean, there's like calculations and stuff, but conceptually, this is all you need to know about Calculus 1, I mean, more or less. Okay, turning back to our example. So here I sort of recolored the graph of f prime to indicate in blue where f prime is increasing, and in red where f prime is decreasing. So here, f prime increasing, and here f prime decreasing. Or in other words, I've indicated if you draw a sort of graph over here of f double prime, I've indicated where f double prime is positive in the blue and where f double prime is negative in the red. So positive, so f double prime is positive here because f prime is increasing. F double prime is negative here because f prime is decreasing. Double prime is positive because f prime is increasing. All right, so after all that color coding, what the second half of the box tells us is that f is concave up, or smiley face, if you want to get technical again, in the blue region, and that f is concave down, or frowny face, in the red region. So again, we're sort of keeping to that basic sketch of this stick figure, but I'm sort of filling in each stick figure piece with a sort of decreasing. So here you go, decreasing smiley face, increasing smiley face, increasing frowny face, increasing smiley face. And remember, increasing and decreasing can be paired with smiley face and frowny face arbitrarily. It sort of gets so technical on you with this whole smiley face, frowny face business. But there it is. Yay! So we've pretty much reconstructed the graph of f from f prime. Just to go over a few more aspects of that coming from the second derivative. We have the second derivative test for minima and maxima. So this test can be easier to use than the first derivative test, especially if you have a formula for f. You just have to sort of solve an equation. So and plug something in. So let c be a critical number for f such that f double prime of c exists. Then the second derivative test says one of three things. If f double prime of c is positive, then for x nearby c, you have a smiley face, which means that f is a local min at c, because look, at the bottom of a smiley face is a local min. If f double prime of c is negative, then you have a frowny face near c, which means that f has a local max at c, because look at a frowny face, at the top of that you have a local max. And here's the really unfortunate thing about the second derivative test, and so you do have to worry about this, is that f double prime of c is 0, then you can't conclude anything, and then you have to just try some other test. So it's not like you can conclude that neither of those things happen. What you can conclude is that you have to try something more difficult. So coming back to our example, let me show you how that goes in practice. So here, remember, our critical numbers were x equals 1 and x equals 3. And we saw from before that f double prime of 1 was positive and f double prime of 3 is 0, because we're going from negative to positive here. And so at x equals 1, f is making a smiley face, which means we have a local min. There it is. And at x equals 3, well, you can't really draw any conclusion from the second derivative test, because when the second derivative at the critical number is 0, well, you got to try something else, man. And you can't really conclude anything one way or the other. However, let me remind you from before that the first derivative test, which told us that that f prime was, because f prime was positive before and positive afterwards, that f has neither a local min nor a local max at x equals 3. That still works. So I guess the sort of if you like the second derivative test, you should still keep in mind that in case of emergency break glass, you can always use the first derivative test if the second derivative test gives you something inconclusive. Oh, one last bit of terminology and something to look for in a graph is an inflection point. So to say that f has an inflection point at x equals c means that f double prime changes sign, sign, sign at x equals c, either plus to minus or minus to plus. So equivalently by the box, so how does this go again? So f double prime is positive means f prime is increasing, and f double prime is negative means f prime is decreasing. So equivalently by the box, an inflection point is where f prime changes from increasing to decreasing, or the other way around. And again, going in the sort of last half the right-hand side of the box, an inflection point is also where f changes from concave up to concave down, or the other way around. So returning to our example, here we can see that because the colors that we've chosen change at x equals 2 and x equals 3 from blue to red, so f has inflection points at x equals 2 and x equals 3. You can sort of see that you make this change from concave up to concave down, or concave down to concave up. And yeah, so anyway, so f has inflection points there for either of the aforementioned, any of the aforementioned reasons. So concavity, we can see over here, f prime increasing to decreasing, or decreasing to increasing over here. And over here, we see that f double prime going from positive to negative, or negative to positive, also indicates an inflection point. Whew. Okay, so that's pretty much what we can get out of f prime in terms of the graph of f at this point. So then the other thing I wanted to talk about is that what can we not figure out about f given f prime? Because it does look like we can recover a lot about f from f prime, but not everything. So one problem is that at best, as we'll explain in a minute, that we can only figure out f up to adding a constant. And so that's actually something sort of that you can't really fix, as we'll see in a minute, but it's not such a big problem. A bigger problem, but one that we eventually will be able to fix, at least if you go through calculus 2, is that we know when f increases and decreases. Let's see, you can see we can figure out from f prime when f increases and decreases, but we don't know by how much, or at least not yet. Okay, so to be specific, turning back to our example, so if c is a constant, then f of x and f of x plus c have the same derivative, f prime of x. So at best, the best you could possibly hope for in terms of recovering f from f prime is if you can get f up to adding a constant. Because if I take this, suppose I drew this f, and by some miracle, the slope of every point on this graph were equal to f prime, the f prime that we started out with. Well, if I take that same graph and I move it up 26 units, the slopes are still the same, and so you really can't get a full solution. You can only get a solution up to adding a constant. The more interesting problem is that given f prime, at least so far, we can tell when f is increasing or decreasing. So remember, f prime is positive means f is increasing, and f prime is negative means that f is decreasing. But we can't yet tell how much yet. No, okay, so as promised, this is something that will show up in calculus 2. Stay tuned for I'll say the secret words. Spoiler alert, the fundamental theorem of calculus. All right, and that will sort of give an answer to by how much. All right, so that's a long one, so go do something useful now. Thank you very much. Bye.